Bismillahirrahmanirrahim and Assalamu alaikum dear students. Welcome to our next lecture. Today we are going to start chapter 5 of our book that is related to the multivariate methods, how those methods could be used for the regression and for classification purpose. Let we look at the background of this discussion. In this chapter we discuss classification and regression which involves more than two variables. Previously we have been working with one variable or two variables. However, now we will be considering a generalized case where more than two variables would be involved in the processing. A data set consisting of d features and n samples can be represented as this, where each x consists of d samples or d features. For example, we can consider the data set of flowers which we have worked out in some previous lectures, which was related to finding the class of the flower data set, and the feature were given in the form of the sepal length, sepal width, petal length, petal width. So, in this kind of data set there are d features which could be called features or inputs for single instance or attributes of our data, and there are n independent examples or events or observations or instances that we want to work with. Such a data set could be represented in this form, where x11, the first row, represents a first instance of our input, and x1 up to xd represents the features or the inputs or the attributes of one first instance. Similarly, for nth instance we still have d features. So, in this way you can understand how our data set looks like. The features may be numeric or the nominal and on different scale. For example, one feature is, let us say that we take some hypothetical kind of data where one feature is age, other feature is salary, other feature is, for example, car, other feature that may be, let us say that we say the temperature, and so on. So, in this case you can consider that each instance, each feature has separate type of values, where age may range from 0 to 100, and salary it may be represented in years, salary is represented in rupees which may have a different range, car is represented as a nominal which represents the classes of the cars. Let us say there are three types of classes, so these values would be 3, 1, 2, 3, and temperature could be represented in the form of the Fahrenheit or centigrades. So, each of these four values have separate scale and separate values for each feature. Usually these variables or the features are correlated. This is very interesting point. If the features are very much correlated with each other, so they contain little information. However, if there is the variability or the small correlation, they contain more information. If they are not correlated, there is no need data analysis. This is another thing, right. So, if there is no correlation at all, then we do not need to have an analysis, and we cannot predict about the things. We know that if some person is purchasing milk, it may be possible that he would like to purchase the tea and other relevant things. So, there is some kind of relationship between the things. If there is no relation at all, we cannot perform any data analysis. We find the patterns when we are performing the data analysis. We find the patterns, mean we find the relationships between the data items, so that we can predict based on that relationship in future when some value is given, and we can find out the destination value for that. Classification and regression are the two problems that we have already seen. A classification is, so in classification the predicted value is discrete, whereas in regression the predicted value is normally a real value. Parametric estimation, as we have seen previously that we can estimate the parameters of the distribution with the help of sample data that we have in hand. So, now previously we have been estimating the mean and the variance, but now as we are working with the variables, with the data which has more than two features or more than one features, so there would be more than one parameters for one type of parameter. For example, for mean value we would not calculate a single mean, instead we will calculate a mean vector, a group of means that if we take the case of this data set, there would be mu1, mu2, mu-d, and data set consists of d features. So, there would be d means, each mean would correspond to one feature. So, it is the mean of each column or feature, where mu I represents the mean of ith column. So, this must be understandable for you that instead of having one value of mean, we would have the d value and each value would correspond to one feature. Variance of xi similarly is denoted as the sigma I, because we would be finding multiple variances just like multiple means. Covariance of xi and xj is given as, now let us say that we may have the values x1, x2, x3, x4. So, to find the variance of x1 with x1, it is known as covariance, or x1 with x2 or x1 with x3 and so on. So, the covariance mean that the variance between two variables or two features xi and xj that could be calculated with the help of this formula. We do not go into the detail that how this formula have been calculated. However, we must note that this formula is used for this purpose. Again, it is also easy to see that previously when we were working with the variance, we were getting the distance of the mean from the given value and it gives us the variance. However, here we are working with the two variables with the two features. So, we will be using the two means given like this and we find its expected value, which is an average value basically. And because we find the covariance of each feature with other feature, in a result we form a matrix of covariances, right. So, there are d variances, diagonal terms, these are the variances where each variable or each feature is processed with itself. So, this sigma 1 1 tells us that what is the variance of feature 1 with itself. Here, however, this tells that what is the variance of feature 1 with feature 2, and this final term tells us that the variance of feature 1 and feature d. There are d features and there are d into d minus 1 over 2 covariances, all of the entries which are off the diagonal basically. So, these are the covariances, and this covariance matrix could be represented with the help of this formula. Covariance of x could be given as x minus mu t e of x into xt minus mu into mu t when we are working with the same variable, and if we are working with different features, then we will use this formula. These two matrices are same, just with the difference that this sigma y 1 1 is simplified as sigma 1 square. So, I hope that two concepts are very much clear to you people on this slide. Number one, we will not find a single mean, instead we will find a group of means, each mean for each feature, and we will not find a one variance, but we will find a set of variances, a matrix of variances, which will be given like this with the help of this matrix. If two variables x and y, two features, for example, we can say that age and salary, for example, we can say that are related in linear way, the relationship will be positive if the slope is positive, right, and the relationship will be negative if the slope is negative. Here the first one, the top figure, shows you a positive relationship, whereas the lower figure shows you the negative relationship. So you must be able to understand that what is a positive relationship and what is a negative relationship. For example, here we can say that with the increase in age, the salary is increasing, so it is a positive relationship. And here we can say that with the increase in age, the salary is decreasing. This is a negative relationship. The size of relationship is difficult to interpret due to varying units of variable measurements. Of course, because age and income have the very different units, so we will find some other statistics about them. One of them is correlation. Correlation, it is a statistic normalized between -1 and 1 and given with the help of this formula. The correlation coefficient is denoted as rho ij, that is equal to the variance of feature I with the feature j divided by variance of I and variance of j. So this is normalizing factor basically, right, of this value. So we can say that it is a statistic normalized between -1 and 1. For two independent variables, correlation and covariance will be 0. Of course, if two variables are independent and there is no relationship between them, so there would be no correlation. Converse is not true. This is interesting. Mean that if there is no correlation between two variables or between two features, it does not mean that they are independent. On this slide, you can again see the correlation. For example, in the first top left figure, you can see a strong positive correlation. The variable on x and the variable on y, all the data points have very much positive correlation and they are aligned with each other. However, in the middle upper figure, which is this, you can see that a weak positive correlation. Again, with the increase of x value, y value is increasing, so there is a positive correlation. And in the right top figure, this, you can see that there is a negative relationship. With the increase of one variable, the value of other variable is decreasing. And here you can see that it is a strong negative relationship, correlation, it is a weak negative correlation. And here we can see that a moderate negative correlation. And here you can see that there is no correlation at all. Everything is random, uncorrelated, independent. So this figure gives you a clear picture about the positive, negative relationship and their degree of positivity and negativity, negative correlation. Again, this shows that a positive covariance and this shows a negative covariance. What is a covariance? We see that what is the variance of x and y. The variance of x and y is known as covariance. So as the value of x increases, the value of y also increases, and that is interrelated with each other. However, here as the value of x increases, the value of y decreases, but the value is interrelated with each other. So there is the relationship, there is the covariance, right? And this picture gives you a clear idea about the covariance. What is that? Maximum likelihood estimate for mu is m. We have seen that if we want to find the mean of the population, we can use the mean of the sample to estimate the mu, and m is given with the help of this formula. And if we are working with multiple samples, so and there are multiple features, so in that case there would be multiple sample means which are given with the help of this formula for all d features. Sample covariance is estimator for the population covariance. It is similar in the similar way where we can use the sample variance to estimate the population variance. So here we use the sample covariance to estimate the population covariance. It is covariance of sample and is estimator for the covariances, correlation and covariance of each feature. This is a covariance of feature I with itself, and this is a covariance of feature I with j. You must remember the formulas that we use to calculate these statistics. Sample correlation coefficient could be given like this. It's just like the previous formula where we have used and we have calculated rho ij, right, which was given like this: sigma I, it was sigma ij divided by sigma I and sigma j. So same formula is given here, but this is for the sample and it was for the population. In order to refresh the ideas about the formulas, refresh the formulas in your mind, here the formulas are given again. Variance is calculated using this formula, covariance is calculated using this formula, correlation is calculated using this formula, and in the last lecture we have seen R square statistic which could be calculated using this formula. So I hope all the concepts given in this slide are clear to you people. Here we use same flower data set to find the relationship of each feature with the other feature. Here you can see that this is the sample length and this is the sample length. So this is something like this: covariance of sample length with itself, and it is the covariance of sample length with sample width. On x-axis there is sample length, on y-axis there is sample width. Similarly, here you can see that this is the covariance of sample length and pattern length. This is the covariance of sample length and pattern width, and similarly others. All the entries which are on the diagonal are the variances because they belong to the same feature. There would be a good exercise that if you download the flower iris flower data set and draw these plots for it. There is a very good library called Seaborn which can draw these beautiful attractive graphs for you people. So try to use that data set to draw this figure in Python yourself. It would give you a good idea that how different data sets could be used to find out different statistics. And this is the same exercise that I have discussed. Estimation of missing values. The data set which you have, the sample that you get to work with may contain missing values, may contain erroneous values, may contain some outliers. So in that case, a data set may contain missing values for different features. There are different strategies we can opt to deal with these values. One of them is discard the records with missing values. A record which contain a missing value for any feature, you just throw it out. But in that case, we will make the data set size smaller, and even it may be smaller than the required data set. Discarding such records will reduce the data set size. there is some information present in such a record that we cannot miss. Another point, for example, if a record which consists of 4 features, the value of 3 features is given and the 4th is not given, if we discard that record, the information that it provides us about the 3 features would be removed from the data set, and we will have less information to work with. Due to these 2 reasons, it is not recommended to discard the records that have the missing values for 1 or more features. Another solution is imputation. Imputation is fill the missing values by estimating them. There are different ways to estimate. For example, one of them is mean imputation. In that, for numeric values, we replace missing values with the mean values of rest of the values for that feature. For example, if the data is given for sepal length, sepal width, petal length, petal width, and in one record or in some record petal length is missing, what we will do, we will calculate the mean of all values of petal length for all of the instances, and that mean would be used in the missing state, right. If here is, for example, this is feature 1 column, and let us say that this is feature 2 column, and let us say that this is feature 3 column, right, and in this case let us say this value is missing. So what we will do, we will take the average of all other values of this feature, and find its mean. The mean would be plugged here. It is a mean imputation. For categorical data, we will replace the missing value with the most likely data. For example, if we have here a field which is called the car, and there are 3 types of cars, if the value of car is missing, we will see that which value of car is mostly occurring in our that feature column. The most occurring value of the car would be placed here. And another approach is regression imputation. We will use the regression to find the missing value for given case, and we know how the regression could be calculated. However, all type of values cannot be imputed. For example, if there is a field which contains the values of C and IC, we cannot impute it. In that case, we are forced to keep it as blank value, or we try to find some other ways to fill this value, right. For example, we may take a value which consists of all zeros in case of missing C and IC. So we keep a special value to replace on this missing feature value. Multivariate normal distribution. Now you have observed that we have been discussing mostly about the normal distribution, because taking an assumption about any data as normally distributed is most likely estimate. In other words, most of the data that we work with is usually normally distributed. So that's why we make the assumption of normal distribution. Single variate and multivariate normal distribution. Single variate linear model could be given like this. We have already seen this in previous lectures, and multivariate linear model could be given with the help of this polynomial. We have also seen such an example previously. And again, it is a linear model because no feature has its power greater than 1. All of the features have the power equal to 1. Although the number of parameters which are denoted by W are increased, the model has become complex, still it is a linear, and its total effect would be in the form of a line when we draw it on the graph. A single variate normal distribution could be given with the help of this formula, and we have already seen this formula. You see that here minus sign is included in this formula, right. Someone was having confusion with this minus sign, that from where it has emerged. Here you can see that this is the part of formula. And shorthand notation of the univariate normal distribution is this. Instead of writing all this formula, we can just write like this to give a shorthand notation of this formula. And multivariate normal distribution is given like this. Here you can see that this is a kind of variance or standard deviation from the mean. You can say that it is a standard deviation, and here we say that because we are working more than two features or more than one feature, so we have all I and j means with it, and we work with this like this. And here in multivariate normal distribution we use one variance, but as we have seen on the previous slides, when we are working with the multi-feature data set, we do not have a one variance. Instead, we have a group of variances that could be represented in the form of matrix. So, this matrix variance is listed over here and again here as well. This is equal to this, right. So, keep this in mind. And 2 pi d, we write here d, which represents, d represents the number of features. Here it was only one feature, and here we have d features, a large number of features. And in short way we can represent this like this. So, this formula in short notation could be given like this: X, the data set that belongs to normally distributed d dimensional data set that has set of means, group of means, and a group matrix of variances or covariances. The distance for univariate data, it is the distance of a point from some reference point. Here you can see that if we have a reference point A and we see a point B, so the distance between the 2 points, the shortest this vector represents the shortest distance between the 2 points. For a univariate data, the distance can be measured in terms of standard deviation. Univariate data could be given as y is equal to ax plus b or this, and we have been using this formula in previous lectures. Such distance can also be give information about distribution. For normal distribution, there is more change to observe a value at one standard deviation distance than two standard deviation. Previously, we have seen that if we know about the mean value, there is more chance to find a given value in one standard deviation distance than to find the value in two standard deviation, right? Because again we see that the area covered by one standard deviation is more than the area covered by two standard deviation. This is the area covered by one standard deviation, and this is the area which is covered by two standard deviations, and the area covered by two standard deviation is small in size as compared to the area covered by one standard deviation. It means that if you are given a value to locate inside this distribution, there is more chance that it would be found out in the one standard deviation distance, and there would be less chance to find it in the two standard deviation, and there will be less chance to find it in the third standard deviation distance. And we have also seen an example related to it in some of our previous lectures. For normal distribution, such a score can be calculated in the term of z-score, the distance of a point from mean. Now try to understand that what is a z-score. Z-score is the distance given in term of standard deviation from mean, right. Look at this, the distance from mean given in terms of standard deviation. So try to understand that what is a z-score. If you have the good idea about z-score, good concept, you would better be able to understand the coming things. Now we look at the distance of the multivariate data. multivariate linear distribution can be given as in general form like this. Again, we are working with a data that consists of more than one features, and again the relationship of those features is linear, so that could be given in this form. A bivariate linear distribution can be given as this. This is a bivariate because we have two features x1 and x2, but still they are linearly related to with each other. The probability density is high for inner contour. Here you can see that it is the same picture that we have discussed in the previous slide. In the case of normal distribution, in the center where the mean lies, there are more chances a value could occur over there. However, as we move away from the mean, there is less chance for a value to occur, and the same thing I have discussed in the previous slide. 2 points in red are shown top and right. In this figure you can see that we have 2 points given in red. The point 1 is 4.2, sorry, this is point 1 which is 0 over 2, x has 0 value and y has 2 value, and this point has 4 over 0, x is at 4 location and y is at 0 location. Now question is that which point is closer to the origin, right? This is very interesting. By just looking at our previous discussions or the previous knowledge, we would say that this point is closer to this origin. However, this is not true. What is the true? Now look at this. If we consider the standard deviation distances, here we have 1, for example, we have 2, we have 3 and we have 4. So we can find this red point after 4 standard deviation distance, but in this direction we have 1, 2, 3, 4, 5, 6, 7. So we find 7 standard deviation distance on this direction. It means that this red point is far away from the origin as compared to this red point. So now you can understand that what this answer is. It depends how you measure the distance. Euclidean distance 4 over 2, this is the same thing that we have seen in the previous slide. We have this red and this red 2 points. This point is present from the mean, if this is the mean, at 1 standard deviation, whereas on this side it presents on 4 standard deviation. So this point is very away from the mean. In standard deviation units, along y axis variance is small distance in 4 standard deviations, and along x axis the variance is more and it has 1 standard deviation. So the point 4 over 0 is closer if we consider the Euclidean distance, but if we consider the standard deviation distances, then this point is closer. In Euclidean, I write here U mean Euclidean and I write here S means standard deviation. So if we measure the distance and standard deviations, then this point, this red point is closer to the mean. However, if we measure the distance in Euclidean points, this point is closer to the mean. The ellipses are known as the probability contours, right? Now we look at another kind of distance which is known as Mahalanobis distance. Probability contours can be used to define the Mahalanobis distance, right? Okay, this Mahalanobis distance is given by Dr. Mahalanobis, an Indian researcher, right? You can find about this guy on the internet, on Wikipedia and somewhere else. Probability contours that we have seen in the previous slide can be used to define the Mahalanobis distance, and here you can see that these probability contours are given, and you can see that this is a center point. So from this center point you are here at the 1 standard deviation distance, and here you are at the 2 standard deviation distance. Similarly, in this way you have 1 standard deviation distance, 2 standard deviation distance, 1 standard deviation distance, 2 standard deviation distance, and here similarly in this way. Remember that when we are working with the one dimensional data, so we have this kind of slope, right? and we cannot have the probability contour, we would have only this surface. However, if we are working with a data which contains at least two features or two variables, then this makes this kind of figure, right. You can see that this is two dimensional, one is in this way and other is in this way. So, in both ways it is normally distributed, and here you can see that how from this figure the probability contours are formed on the plane. So, it is in space, in 3D space, and here it is in 2D space, 2D plane. And similarly you can get the concept from here. If we slice it from here, so it would be a two dimensional thing, right, that would lie on the in space, not in plane. Okay, so we understand that what is the probability contour and how they are interpreted and represented. And here you can again see that these are the two probability contours. Both in this case there is a variance, one variance in this way along x axis and other variance in this way along y axis. So, there are two variances now, and here again you can see that we have one variance this way and one variance this way. The variance toward this upper side where I have drawn the arrow, that is greater as compared to the variance which is given toward the lower side. It accounts for the fact that the variance in each direction are different. So, you can see that from this figure that variance in each direction is different. It accounts for the covariance between variables. The Mahalanobis distance covers this fact, it covers this fact, it reduces to the formal Euclidean distance for uncorrelated variable with unit variance. This is interesting. If there is the data which is uncorrelated, then they would have nothing like this variance I, variance j, only there would be variance I and variance j, standard deviation this end, right. So, in that case it would reduce to Euclidean distance. So, Mahalanobis distance we can consider it as an extension of the Euclidean distance. Mahalanobis distance, the distance x is d-dimensional and normally distributed. One fact about Mahalanobis distance, and if x is normally distributed d-dimensional data with mu as mean vector, this is a vector which is a group of means for each sample for each feature, and this is a covariance matrix, Mahalanobis distance could be given as this. In multivariate cases this distance is used and given by this formula, right. We will work out on basically this formula in multidimensional, we work with it. So, P of x 1 over 2 pi d by 2 and this, right. Here over 2 is given in the place of, if we give the under root symbol over here, then this 2 would be removed and we come up with the same formula that we have seen in the previous slide. However, as we have taken out this under root, so this 1 over 2 is used, and this, right, this is an extension of the simple univariate normal distribution. Mahalanobis distance is the d-dimensional hyperellipsoid centered at mu, and its shape and orientation are defined by this, the covariance matrix. Of course, it is defined by this, because if the variance between two features is less and in one dimension it is less and other dimension it is higher, then these kind of ellipses could be found. And if both variances are equal, then we can have this kind of figure that we have seen on the previous slide. If a variable has a larger variance than another, it receives less weight. Two highly correlated variables do not contribute as much as two less correlated variables. The use of this matrix thus has the effect of standardizing all variables to the unit variance and eliminating the correlation. So, this could be seen used over here. When it's taken above, when it comes above, it would be like this. So try to understand that what is a Mahalanobis distance, right? When we are working, now this is very interesting. When we are working multidimensional data, we will find Mahalanobis distance to find out how much one data instance is near to other data instance. Example, bivariate normal distribution. Bivariate where the case where there are two dimensions, two features. For independent variable, major axis of the density is parallel to the x-axis, input axis, right? Look at here now, this figure. Here, this is the independent variable x1 and this is dependent variable x2. So their covariance of x1 and x2 is equal to 0, and variance of x1 is variance of x2. For example, in this direction we will find the variance of x1, and in this direction there is the variance of x2, right? I draw it with the help of two different colors to make the idea clear. Vertically there is a variance of variable x2, and horizontally there is the variance of variable x1, and both are equal. In this second figure, you can see that variance of along y direction of x2 is smaller as compared to the variance of along x direction of x1. And here you can see that covariance of x1 and x2 is greater than 0. Try to understand that how, if we are here, right, how the values are changing. And similarly, you can also have the view of this. It means that different values of covariances would make the ellipses of different shape, right? And here you can see that how the ellipses are formed from this. So this is a two-dimensional normal distribution, this figure. Bivariate normal distribution, we continue the discussion. For independent variables, the major axes of the density are parallel to the input axis. This is the point that we have already seen in the previous slide. Major axis, longest diameter in the ellipses. For example, in this case, this is the major axis and this is the minor axis. In this case, this is the major axis, right, and this is the minor axis, right. The density becomes an ellipse if the variances are different. If we have different variances, of course, instead of circles, there would be ellipses. The density rotates depending upon the sign of the covariance. The center is given by mean and shape orientation by covariance matrix. Of course, the center of this is given by the mean and the shape of ellipses is given by the covariance matrix. Try to understand this concept. Joint bivariate normal distribution. We are continuing the discussion of bivariate normal distribution, where we have two features, two variables. So mean vector is then given by with the help of μ1 and μ2, and covariance vector is given by this, right. Joint variate density is given by this formula. Z normalization. The process of making mean 0 and unit standard deviation of input variable is called Z normalization, and basically we have seen this as well previously. We take the Z over here and we will get this over here. So Z score, how that is found. It is known as Z normalization. Effect of values of correlation coefficients rho that we have been using here and here. Correlation coefficient. It is also being used over here and here. This is a value that we use, right, and this represents if the value of rho is less than 1, the absolute value of rho is less than 1, it means that P x1 x2, the giant probability distribution, is the equation of ellipses. If rho is greater than 1, major axes of ellipses have positive slope. This is a positive slope. And if rho is less than 1, major axis has the negative slope. So from the value of rho we can tell something about the orientation and shape of ellipses. Continuing the bivariate case, each variable is normalized to have unit variance. There is the cross term that corrects the correlation between the two variables. Right here you can see that we have one here variable, other here, and these are the covariances. There are 5 parameters in this case, in this equation: mu1, mu2, sigma 1, sigma 2, and rho. Sigma, the covariance matrix is non-singular and hence positive definite provided with the variance are non-zero, and rho is given by this. So interestingly, you can see that the covariance matrix is represented with the help of these values. Try to understand that how that is represented with the help of these values. If rho is +1 or -1, the two variables are linearly related. The observations are effectively one dimensional, and one of two variances can be disposed of. Right? If rho is either 1 or -1, the two variables are linearly related with each other, so we can drop one variable because the same information could be taken from the second variable. And if rho is 0, then the two variables are independent, the cross term disappears, and we get a product of two univariate densities. Right? So if rho is 0, so we come up with 1 only, and the under root of 1 is 1, so this disappears basically, and here it also disappears. Right? Here it also disappears. Univariate interpretations. In univariate case, small value of variance indicates that samples are close to mean, and variance of x is greater than 0 in univariate interpretation. And in multivariate interpretation, in multivariate case, small values of the covariance matrix entries indicate that samples are close to the mean vector, where this mean vector is given by this. Now try to understand this concept in try to match these 2 points. The sigma, this summation is a symmetric positive definite matrix. Small values in this may also indicate that there is a high correlation between variables, right? So again look at that. And if x belongs to normally distributed data set of d dimension, then each dimension of x is univariate normal. This is very much interesting, that if say that we have feature 1, feature 2, and feature 3 in our data set, each feature is itself univariate normal. However, if each xi, the feature, may be univariate normal and x may not be multivariate normal. That's interesting. It says that this feature is univariate normal itself. However, as a combined set, it may not be multivariate normal. So try to understand these facts about the univariate and the multivariate interpretations. Naive case of multivariate normal. In the component, if the components of x are independent and covariance of x and y is 0, of course, if the components, all the features are independent, for example, if there are two features I and j and they are independent of each other, then their covariance is 0 for I = j, and their variance is given with the help of this, right, like this. Then the covariance matrix is diagonal and the joint density is the product of the individual univariate densities. Here it is interesting that if all of our features fulfill these properties, then only the diagonal variances would exist and covariances all would be 0. right? And we can just think that this and all these are independent of each other. When they are independent of each other, their probabilities could be multiplied. So we can write it like this: the probabilities of all the independent features are multiplied with each other, and if they are normal, then we can write this formula for this, right? So try to understand this formula as well. Let X belongs to n-dimensional normally distributed data and W the set of parameters that belong to a d-dimensional real numbers, then WTX could be written as this, right? This is the linear multidimensional relationship, and it belongs to normally distributed data, right, where this is the weighted mean and weighted variance. Expected value of WTX is equal to WT EFX, where EFX is mu, so we write WT mu, and variance WTX is given as WTX minus WT mu, because we know that if we take out this WT, this is the formula of the variance, we have just introduced WT with it, and applying the expected value on it and expanding, we get this value, right? Further we can simplify here, and it becomes finally this, right? Here we can see that the covariance matrix has been used. Look at this and try to understand that how the covariance matrix has come up. The projection of d-dimensional normal on the vector W is univariate normal, right? It means that if we transform the d-dimensional data into W, which is a univariate normal, then it is a projection, right? How this is, for example, we have feature 1, we have feature 2, we have feature 3, we have feature 4 of our data. This is a multivariate d-dimensional data, 4-dimensional data, and we want to predict their class here, which is a univariate. So we project all these things on this, right? So the projection of d-dimensional normal on the vector W is again normal, but it is a univariate. So if this is normal, right, this would also be normal. This point shows this fact. In general, if W is a D cross K matrix with rank K, which is less than the number of dimensions of our data, then K dimensional WTX is K variate normal, right? So in that case, the number of dimension would determine the variation of the normal data, normality. In general, okay, so we have seen this, that WTX belongs to NK WT mu, WT sigma mu, right? WT is just a weighting factor or the set of parameters that we are associating with our data. It means that the simple is the case. If the data is normal, the parameter would also be normal. If we project a d-dimensional normal distribution to a space that is k-dimensional, then it projects a k-dimensional normal. What it says, it's very interesting. If we have a d-dimensional data and we project it, mean we transform it into one-dimensional data, just like that we have 1, 2, 3 and 4 dimensions, and we want to predict its class. So if this is normal, this one dimensional would be a univariate normal. It's a d-dimensional normal, it would be univariate normal. However, if this is projected to some k dimensions which is less than this d, in other words, we are reducing the dimension, let's say that d is 4 and we want to project it into 2 dimension, then this would be 2 dimension normal. This is n dimension normal, this would be 2 dimension normal. In general, if we project n dimensional normal to any other space which is k dimensional, where k could be 1, 2 or 3, whatever the dimensions we decide, that would also be normal. Try to understand this point. And here is an exercise that I give for you people to do it on yourself. Again, do it through the programming, right? Flower data set, iris flower data set could work for this exercise. This is today's lecture. I hope you got the concept that I have explained. You would understand it. Read it, practice it, read the book. See you next time in next lecture. Till then, Allah Hafiz.